class recording has started. So if you would like to say anything incriminating about yourself, please refrain from doing so. Well, unless you want to get caught, I suppose. But anyway, all right. For today, as I just stated, we wanted to take some time and go over some concepts dealing with circular motion, what causes the circular motion, what's required to make something go in a circle, those sort of things. And hopefully by the end of the period, we will get into our next topic dealing with circular motion, that being centrifugal force. We introduced centripetal force with a P earlier in the unit, but today we'll hopefully get to centrifugal force with an F, talk about how they're similar, how they're different, what's really going on. Okay? First, as far as the calendar goes, yesterday you guys took your quiz. I have not graded the quiz yet. Also, if you have not turned in your lab where we ran the hover pucks into one another, please make sure that gets into me sometime in the near future as well. Okay? Monday, we introduced circular motion, centripetal acceleration, centripetal force. Today, we'll deal with some of those concepts and problems. Tomorrow and Friday, we will gather data for the lab dealing with centripetal force. Not a LabQuest lab, good old stopwatches and meter sticks. So we'll do that lab tomorrow. We'll collect data Thursday. We'll do calculations and questions on Friday. So you have 2 days to work on that lab in class. Then, next week, when we are on OGT schedule, we will have a half an hour each day. And that's good. We'll do problems next week. So would that be good? We'll introduce like one kind of problem a day, do like one example or 2 examples in class, and that'll get us through the week. Friday, I have a built-in day sort of for us to wrap things up if we need to spill over a little bit because one took longer than others or whatever. Okay? Then the following week, March 18th, we'll review in class, and then March 19th, test. That will be your last grade for the 3rd grading period as it ends March 20th. I think we discussed in class that I do have a couple of days to finalize grades, so corrections will be available to you on that test. Okay. Good there? On Monday, we talked about centripetal acceleration and centripetal force. And we said that this situation here, an object moving in a circular path, is not a natural thing. Why are circles or circular motion not a natural thing? Inertia. Because of inertia, right? Inertia is telling things to do what? Go straight, right? Like this water that's coming off the grind wheel, or these sparks that are coming off this grinder wheel here, right? Circles are not natural things. Circles result from acceleration, and acceleration results from force. And that acceleration that we discussed was called centripetal acceleration. If an object has an acceleration that is pointing towards the center of rotation, which happens to be perpendicular to its current velocity, it will move in a circular path. Inertia is telling it to go this way. Centripetal acceleration is telling it to go this way. The end result is somewhere in the middle. Depending on how big the acceleration is and how fast the velocity is, that will determine the kind of circle that this object goes in. Okay? But we also talked the idea that if there's acceleration, there also has to be force. So centripetal acceleration is caused by centripetal force. Centripetal force is an unbalanced force because it's causing acceleration. Things that are balanced out won't cause circular motion. They'll cause equilibrium, and that's not a circle. Right? Good there, as far as that goes? So we said also that centripetal force is not some new kind of force. It's a force that we already know about, but it's acting in a specific way, that being perpendicular to the motion of the object, which causes the circular motion. Okay. Good there? All right. With that being said, let's start off with some textbook questions. Like I said, if you have your cell phone, I appreciate it if you participate, just because it lets me get some feedback and lets me know how people are doing and people are understanding these concepts. Okay? There are several spelling errors, so I will try to point them out as we go along. But the first one is pretty easy. Hopefully you'll think it'll be easy as well.
Is this the same website?
Say again?
Is this the same website?
Yeah. Why does it look different? Or?
Yeah, it's bottom.
was a little different on the bottom. So the first one, this one actually, oh, go ahead. Car travels around a curve at a constant speed. This car is accelerating. True or false? So just in case you don't remember, right? This code 37607, that's what you put in the to line. Most of you might have it in your contacts already, and then in the body of the text message, you just write this six-digit code. Don't write code, or don't write true, or don't write false. Okay? We had several people last period that were not paying attention and did that. Rookies. Totally. So. All right. Yeah. Results are rolling in. Last period we were having some problem with getting a lot of results up here. I don't know if the website was working slowly or what, but
There's not much service.
so, I mean, but as long as the message gets sent, that's just it. All right, 14 results. Nice, nice. Give it another second here before we reveal answers. So, car travels around a curve at a constant speed. This car is accelerating. The correct answer is true. Okay? Yes, it says constant speed here. But what's not constant? The direction is not constant. We talked about earlier in the year that acceleration can take three forms. Speeding up, slowing down. It's not doing either of those, but it is changing direction. So a car traveling around a curve at a constant speed is accelerating. Okay? Good there? The problem set that I gave you today, that looks like this, okay? That was basically question number 1. Okay, so it says a car travels on a curve at constant speed. Does the car experience acceleration? Yes. Why? Because the velocity is changing. Why? Because what does it keep doing continuously? Changing direction. Okay? So if you want to make some notes there, that's fine too. All right. Good there? Text poll question number 2 is not on your sheet. It's a different one. So let's come up here and let's look at question number 2. Question number 2, several spelling errors. Where's blue there? Oh, there. So it says, an object moves around a circle at a constant speed. Which of the following is not true? Which of the following is not true? So it says centripetal acceleration is, it should say is, not if. So centripetal acceleration is perpendicular to its velocity. Okay. Tangential speed is constant. The velocity, not velocity, is constant. There is an unbalanced force acting on the object, or the acceleration of the object points towards the middle of the circle. As you may have figured out here, there is no spell check on this website. So, which of the following 5 statements is not true about an object moving around a circle at a constant speed? Results. Excellent. Thank you for your participation.
Can you text more than once?
No.
You can? Oh, I just tried like 20 times.
What happens if you do?
Probably send you a message back and says, hey, you can't text more than once in this poll. I have it set up that way. I can change it to let people respond more than once, once, but don't really feel the need to do that for this activity. All right, so let's take a look. Okay. Correct answer is the velocity is constant. Okay? So most people said that. Okay. All the other ones are true. First, tangential speed. That's how fast it's going around the outside of the circle. That will be true because it's a speed. Doesn't change how fast it's going. But its velocity is not constant because, as we just discussed from the previous problem, what keeps changing? Direction keeps changing. Okay? As far as the acceleration, like we saw on the slide that opened up class, or that we went to review, the acceleration always points towards the middle of rotation. We call that the centripetal acceleration. And it's always perpendicular to the path the object is currently traveling. And that gets us to the idea of it's trying to go straight, we're trying to tell it to go in the other direction, the end result is somewhere in between that. Okay? But if there's acceleration on that object, what else does there have to be on that object? Force, but more specifically, a unbalanced or a net force. Okay? So centripetal force is a net force because it's not balanced out by something else. Okay? Good there? Text poll question number 3 comes from the problem set. It's question number 2. So first, just for a visual, right? Question number 2 on your problem set says, a ball on the end of the string is whirled counterclockwise in a horizontal circle, as shown from above. So we're looking at this thing from above. The ball is going in this direction, but when it gets to this point right here, the string that it was twirling on breaks. So it says, which of the paths shown is the path that the ball will take? So which of the paths shown from that picture is the path that the ball will take? There's also a misspelling here. At point A, the string holding the ball breaks. Which path does the ball follow? 1, 2, 3, or 4? So you make sure you reference your picture on your problem set here. Which path will the ball take when the string breaks? Last period was not working. Like no responses were coming up. All right. With 16 total responses, take a look. All right. So the correct answer here for the path that the ball will follow is path 3. Okay, path 3. Why? What is path 3? It's straight, right? It's a straight line. It says that if there is no force acting on it, right? Once the string breaks, there is no net force acting on it anymore. If there is no net force, what does it do? Whatever it was doing before, goes straight. Okay? Good there? The next 2 text poll questions come from your problem set. They are problem number 3 and problem number 4. Okay. We'll do them individually, but just for the visual, for the recording. So it says you've got 2 cars and they're going around curves. In the first curve, 2 cars of equal mass travel around the same curve. Car A travels twice as fast as car B. Which one experiences the greater centripetal force? So you're probably going to have to reference your notes from earlier in this week, find a formula for centripetal force, see if you can calculate that out. Okay. Two cars, equal mass, same curve. Car A travels twice as fast as car B. Which one experiences the greater centripetal force? Car A experiences a greater centripetal force. Car B experiences a greater centripetal force. Or they have the same centripetal force. Cars, equal mass, same curve. Car A travels twice as fast as car B. Which one experiences the greater centripetal force? All right. 16 results. Result pulling. So, for question number three, right, deals with centripetal force. Earlier in the week, we introduced the idea of centripetal force as being equal to mv squared over r, right? The mass of the object going around in the circle, how fast is it going around the edge of the circle, the tangential speed, plus, or divided by the radius of that curve. Here it says they have equal mass, same curve, meaning they have the same radius. That means the only factor that's going to determine the centripetal force here is the velocity. Car A twice as fast as car B, so car A will have the greater centripetal force. Specifically, how much more centripetal force? 4 times as much, because we're squaring velocity in that formula. Good there? Okay. The next question relates to question number 4. So if you're reading along on your sheets, or waiting for me to put the question up here on the board, question number 4 from your problem set says, two cars travel with the same tangential speed around 2 different curves. The curve that car A travels around has a radius twice as big as the curve that car B travels around. Which one experiences a greater centripetal force? Even though it doesn't specifically say in this problem, you can assume that those cars have the same mass. So will car A have a greater centripetal force, car B have a greater centripetal force, or they have the same centripetal force? Two cars, even though it doesn't say specifically same mass, same speed, 2 different curves. Curve that car A travels around twice as big as the curve that car B travels around. Greater centripetal force. So, once again, centripetal force, mv squared over r. I told you that the masses were the same, that the velocity was the same, so the only factor that's going to influence the centripetal force here is going to be r. A, twice as big a radius as B, therefore, you make the bottom of this fraction bigger, the amount of forces required is what? Smaller, right? So car B will require the greater centripetal force. Okay? If you think about driving in your car, think about that big loop that you have to go around to get onto the highway, right? Versus turning into your driveway, right? Which one do you have to turn the wheel more? your driveway, right? Because the radius is smaller. Now, granted, the speeds aren't quite the same, but the radius being smaller, that's going to require more force. That's going to require you to turn the wheel a little bit more to create more force there. Okay? Good? All right. Next question is not from the problem set, but it is similar to questions that are on the back of the problem set. This is a short calculation. Somebody already voted. I'm not sure how exactly. Yes. So it says, what it said, this problem is not from your problem set, but it is similar to questions that are from the back of your problem set. It says a car is traveling around a curve with a radius of 25 meters at a constant tangential speed of 15 meters per second. What is the centripetal acceleration of the car? Radius 25 meters, constant tangential speed of 15 meters per second, centripetal acceleration of the car. Might have to find yourself a formula. So. Still not.
Right in your own.
This wasn't an open response question. So.
One of those is right.
One of those is correct.
I'll sit up just take me out, coach.
So.
So.
Car traveling on a curve, radius 25 meters, constant tangential speed. Here it's asking you with centripetal acceleration, which you calculate by v squared over r. It gave you v of 15. It gave you r of 25. You plug that into this equation, you get 9. Okay? Did you really put the 0 up there?
I voted before the question was up there.
I know how exactly.
I
Just typed a random number.
Well, it's had 768, so it's like 4.
That's true. It's probably going in order. So. All right. This one.
It does. They're 11 before.
This one is kind of interesting. Okay, even though Evan jumped the gun, that's why I got it right. But here, they said it is traveling at a constant speed, right? But that doesn't mean acceleration is 0, right? As we've discussed, the direction change results in an acceleration. Okay. Good there? One more question here. Once again, not from your problem set, but a separate question. Nope, no calculator. In regards to the car that we were discussing in the previous problem, what is causing the centripetal acceleration of the car? What causes the centripetal acceleration of the car? Is it the force applied to the steering wheel from the driver's hands? Is it friction between the road and the car's tires? Or is it the normal force acting on the car from the road? What causes the centripetal acceleration of 9 that we calculated in the previous problem? people said it was the friction between the road and the car's tires, and that is correct. All right. These two, the force applied to the steering wheel from the driver's hands and the normal force acting on the car, those two don't prevent the car from going in a straight line. Okay? Normal force, right, it is perpendicular to the way that the car is going, right? If the car is going in this direction, right? If the car is going this way, normal force is acting on it this way. But what else is acting on it in that dimension or in that axis? Gravity, right? So this can't be causing an acceleration because it's balanced out by the gravitational force that's pulling down on it like this. But friction, right? Friction is acting perpendicular to this velocity. It would be like in a third dimension coming out of the board towards you, causing that car to go in a turn like that. Okay? Yeah, I know. Maybe in the new school. So it's three-dimensional.
That'd be pretty sweet.
That would be pretty sweet. You just like project it like in the room, you know. And
Okay, Tony. How would you record that though? That'd be confusing.
you'd have to get 3D glasses to watch it.
That would be awesome.
That would be kind of cool. That would be pretty cool, like Iron Man kind of setup. So that just like
So everyone's coming out.
you know, it's summer, so yeah, looks pretty.
So is Captain America?
It's pretty down. So
Oh, wait a minute.
I still have to say though that of all the Avenger movies, like the original Iron Man, I think is really my favorite.
Yeah.
That's pretty good.
Yeah.
Really was good. So, all right. Enough of that. Are we good there? Okay. So that's good as far as the text polling is concerned. Okay. For the last couple minutes today, I want to talk about the last concept or introductory concept of circular motion. So, if you have a place where you're writing some things down, you might want to pull that out so we can talk about centrifugal force.
What?
Good. Notice the difference in spelling. Centrifugal force, or why does my little brother go flying across the back seat when I turn around a corner in my car?
Because you turn faster if you wanted to.
Yes. That's actually. I got some good animation later on to illustrate this. So. But first, some demonstrations. Water. That sounds good on the recording. Well, here. Seeing as how you requested it, right? And this is, obviously you can't see this on video. Actually, let's try this. I don't think it's going to work, but. Yeah. But the webcam doesn't, usually doesn't show up when I'm recording. It just shows up like it's a big black square on the recording. But we'll try it.
Put this on YouTube.
I mean, these do all end up on YouTube, so.
Classroom 777, this is for you.
Oh.
He's gonna finally find out what you look like.
Be heartily disappointed, probably. So. All right. That's really blurry, so let's see if we can do something about that. No, it's not. It's all right, so here I have a orange plastic circle with a couple of strings attached to it. Okay,
Physics term.
and yeah, this is very like scientific piece of equipment. So, and because Evan requested, here's Batman. So, all right, what? No, his ears have pretty much been chopped off. So here, if you get like kind of look like this, right? You know, okay. So, I'm going to put Batman on top of the orange plastic circle, scientific thingy, okay? And then I'm going to whirl him as such.
Not the
Right?
Dark Knight.
Oh, he's the Dark Knight. He'll be all right. Don't worry. So, okay. All right. 3, 2, 1. No, he'll return in a second. Watch. Ready? Okay. And go. Okay. So, I say you guys are in trouble. I'm not in trouble if he flies off the edge. You guys are though. So, all right. So there he is. Okay. Now I just have to keep doing this till the end of the period because I don't know how to stop it. So I just have to like let it go. So.
Wow, we should have started this earlier.
I know, really, we should have. So I'll have a big rope burn on my finger by then, but okay. All right. So we'll get a little close up here, right?
It's probably sick.
And now he has returned. All right. So there, standing majestically, overlooking Gotham, right? Okay. All right. So there, first demonstration. Okay. Second demonstration. Okay. So big, exactly. So bucket of water. All right. So you guys are in the splash zone here. So
It's not as bad as being in the splash zone for the men. I trust him.
all right. All right. Don't do that. Don't do that. All right. So what is here? Julia, I'm sorry you're going to get in the picture here. So are you 18?
Say hi to Boston.
Yeah, you are.
I was never here and sign a form for this.
Like 2 days.
All right. All right. So here we go. Ready? And go.
Oh.
All right. So. And last but not least, right? So
All together now.
all together now.
Put Batman
Water
in a cup.
Water in a cup.
Batman in a cup.
Yeah.
Maybe we'll just put Batman next to the water on the cup. So.
Will this work?
So.
Someone's gonna get voted off the island.
Double
Okay.
splash zone.
So.
Oh my god.
All right.
Can you get the bucket going on one side?
Actually, I could. So. All right. Actually, this trick I did not try until last period. The first time I ever tried it. All right, and it worked. So. All right. Are we ready?
Maybe. Am I going to die?
Wait.
Batman. Like a
I do get a little head bob. I'm glad you're recording. I don't know if I'm skilled enough for that just yet. All right. So let's talk about the 3 demonstrations that we just did. Okay?
Keep it both, please, at the same time.
What?
I want to see you do both at the same time.
Other than the fact that it's like, witchcraft. Right? So we talked about that this situation right here is not a natural situation, right? Things don't naturally go in a circle. Things naturally go in what direction? Straight line, okay? And I've told you over the past couple of days that when things go in a straight line, there's a force acting on them. How is the force acting on them? Perpendicular. In relation to the circle, where does it point? Towards the center. So we've established that if there's, let's say, something inside of that bucket or that can, like, a ladybug, for instance, okay, right, or water in a bucket, in order for it to go in a circle, it needs to experience a force this way. But if that's the case, what would that suggest that the ladybug would then do? Go towards the center of the circle, at least as far as this picture is concerned, right? But it doesn't, right? Or if you've ridden a ride that goes around in a circle, I know the bell's gonna ring in like a minute, but let me finish this. If you've ridden a ride that goes around like in a circle, right? Where do you always end up? Like on the outside edge, right? You put the small person on the outside edge so they get crushed by everybody else, scramble or whatever it is, right? So that would suggest that perhaps there is a force that pushes outward, right? Like the water that's in the bucket or the ladybug that's in the bucket, right? If it's going to stick inside the bucket, or if that cup is going to stick to the outside edge of the orange circle, that might suggest that there is a force that goes this way. But we'll find out that that's not really the case. Right? Tomorrow we'll talk about why.